In this week, with the midterm drawing closer, I'd like us to review, some of the questions, that we've come across, especially the computational aspects. So I'd like us to pause a little bit, and review some of the problems that we've come across so that all of us are fairly, skilled in being able to solve those problems. I've also posted for you guys some problem sets, and so some of the questions that I'm gonna go through here are those that are selected, from the problem sets to make sure everyone is capable of doing them. And so for the next 1 week, I will not post any new material, but instead, I'm gonna go through some of those problems and we're gonna try to solve them together. Now, remember when we started talking about ppm and parts per billion, and just to refresh your mind, the reason we do this is because when we are doing analytical chemistry, most of the concentrations that we are dealing with are very, very low concentrations. And so remember, we defined, ppm then as, the mass of the substance or the analyte, and you divide it by the mass of the sample, and you multiply that, by 1,000,000. And maybe somebody would ask, where did this come from? This whole concept, comes from multiplying, this equation, by the density. So take note of this, the mass of the substance, if I'll call it that, divided by the mass of the sample, multiplied by the density, which is often in grams per mil. It's gonna give you whatever it is in grams per mil. Okay, now if you're dealing with only 1 ppm, say, of your substance, chances are, the density of such a solution is very, very close to the density of water, and that would be 1 grams, per mil. And as such, you can take, the grams, per mil, and you can convert that to milligrams, which is 10 to power 3 to convert it to milligrams. And then the mils, you can convert this, to liters, which is 10 to power minus 3, liters per mil. And so in the end, you can see this guy becomes about 10 to power 6. You can see if you take 1,000, divide by 0.0001, it becomes 10 to power 6. And actually, that's how we come, to get this relationship. Okay? And then you can see actually, my results here, became milligrams, because these one cancelled out. And then the mils cancelled out, milligrams per liter. And so that explains to you, that essentially ppm is equivalent to, milligrams per liter. So anytime you see milligrams per liter, it's referring to ppm. But also remember, I can, say divide or multiply the top by 1,000 and multiply the bottom by 1,000. And that doesn't change, the relationship. So it's gonna be equals to, the grams, per it's gonna become, the microgram, per mil. So microgram, per mil is exactly the same as milligrams per liter. And equivalently, I can multiply the top by another 1,000, and so that becomes nanogram. And then the bottom, by 1,000, and it becomes, microliters. And so again, ppm is equals to milligrams per liter is equals to microgram per mil, and it's equals to, nanogram per microliter. I hope that's clear. And so anytime you see these relationships, they are referring to exactly the same thing. Now remember, milligrams per liter. If you decide to convert this into grams, 1 liter of an aqueous solution is equals to 1 kilogram. And so essentially milligrams per liter can also be called milligram, per kilogram. So all these, are examples of ppm, are equivalents really, of ppm. On the other hand, when you're talking about, parts per billion, it's referring to what you would call a microgram, what you'd call microgram per liter, so that would be parts per billion. Okay. Which again can be equivalent to, nanogram, per mil. That's again, it's talking about parts per billion. And of course you can keep going on and on, picogram, per microliter is talking about parts per billion as well. And you can see all I'm doing is multiplying the top by 1,000, bottom by 1,000. So another problem, question number 2, you've been asked how many milliliters of concentrated sulfuric acid, and the sulfuric acid you bought it from the manufacturer is 94%, and the density is given, and you are required, to make 0.1 molar solution, from 94% of concentrated acid. So the question is, how many mils of this, do you actually need to make a 0.1 molar in 1 liter? You see, the problem here is you've got the concentration in percent, and so you need to convert that concentration into molar concentration, so that you are able to do the dilution. And so the way you would do that is, the molar concentration of sulfuric acid is gonna be equals to the percent, which is 94 divided by 100. And then you multiply that by the density, and the density is given 1.831 grams per mil, and grams per cubic meters is exactly the same, as grams per mil. And then you're gonna see that you need, of course, to you need to convert, these mils into liters, and so I need to multiply that, by 1,000. So that I can convert, that into liters. And I need to divide everything, by the molar mass. And the molar mass is 98.08 grams per mole. And of course, remember, I'm converting this into liters, which would be like multiplying it with 0.001, and that's the same as multiplying this up there by 1,000. And so when you do that, you're gonna see the molar concentration of the 94% of sulfuric acid is 17.55 moles per liter. And now, knowing this, you can very easily calculate the mils, because you know the dilution equation, C2V2. and the original concentration is 75 molar, and we are looking for the V1. The C2 is known, that is a dilute solution that you are making, and it's 1 liter of solution, which is 1,000 ml. So the V1 then is equals to 5.70 of a ml. However, a very simple equation that you can equivalently use to convert, molar concentration, into percent and vice versa, is the molar concentration is equals to C percent, multiplied by the density, in grams per mil, and then multiplied by 10, divided by the molar mass. So if I were you, I would remember this relationship, and it's fairly easy. And all what you're gonna need to do is substitute this to 94, and then the density in grams per mil to whatever you've got, 1.831, and that's it. Multiplied by 10 is equals, and divided by the molar mass, you'll be able to get this. And so this is the relationship that typically you would use. So the next problem is to calculate, rather than molar concentration, the B, you've been asked to calculate, molality. And molality, with a small m. And remember, that's the molality, of 94% of sulfuric acid. Remember, the definition of molality, is equals to the small m, the moles of the solid, divided by the kilogram of the solvent. And so remember, molality really is what you say is temperature, independent, and that's why it's better, than molar concentration, because you're doing the solvent in kilogram, in mass, and mass is temperature independent. And so the moles of the solid, in this case, for 94% of sulfuric acid, I've got 94 grams of sulfuric acid divided by the molar mass, which is 98.08 grams per mole. And so that's a number of moles. And then I divide everything, by the kilogram of the solvent, which is 1 over, remember the kilogram of the solvent, would be 100. That's a percent, that's a total, minus the 94. And so whatever I get there, which is 6 grams, is gonna be, in the solvent mass. And of course, that's grams. I need to convert it, into kilogram. And of course, the way I do that is to divide it, by 1,000, which is equivalent really to multiplying it by 1,000. And this one is gonna be in kilograms. And so the answer that I actually get then is gonna be, just confirm this, is gonna be 159.73, molality, or molality. So question number 3 is an interesting problem, and maybe a few of you may struggle a little bit with this. Is a back titration, and I'd like us to go through, how you do a back titration type of, volumetric titration. And so you've been given chromium 3+, and because it reacts fairly slow with the titrant, that's why you're doing a back titration, so that you can give it enough time to react. And so you take the chromium, and so pharmaceutical preparation containing chromium 3+ is analyzed by treating a sample. So the sample contains 2.63 grams, and it has chromium. And you're treating it with 5 ml, of this concentration of EDTA. And after you mix it, you allow it to react. And then following the reaction, this whatever didn't react of the EDTA is back titrated with this number of mils of another titrant, in this case, zinc solution. And so the question is, what is the concentration of chromium chloride, in the pharmaceutical preparation in the sample? So what you need to do in this case is always start by writing, the titration reaction. The titration reaction. So the first reaction, you can see I've got, chromium 3+ in my sample. And I'm reacting it with EDTA, ethylene diamine tetraacetic acid. And sometimes people, symbolize EDTA using H4, Y. And actually it's a penta. It's got up to 4 hydronium ions, so we were talking about polyprotic acids, the other day. So this guy has got up to 4 a hydronium ion that can dissociate. That's why you're saying it's H4Y. Okay, and you can see that it is in excess, so we add this in excess, and the products would be the chromium Y-, so it's a complex of EDTA and chromium. It's a complexometric equilibrium, and you're getting the acid sort of as a spectator there. Now the next reaction that is taking place is I'm taking my, and of course here there is also the excess Y-, there's excess EDTA, there's excess EDTA. And so the next reaction that it's taking place is the H4, Y, and this is what remained. Is what remained here. And then I'm reacting that, with the zinc 2+. This is my titrant. And it's giving me, the zinc complex. Plus the acid that dissociated. Not very important in this case, but it's there. Okay, and so what we need to really calculate then is we already know the number of moles of zinc that was used. So we know the number of, and it's a 1-to-1 stoichiometry, we've been told. And you already know the number of moles of zinc, that was used as a titrant. So the moles in this case of zinc is gonna be equals to it's gonna be equals to 1.32, and that's mil, multiplied by its concentration, which is 0.0122. and that's molar concentration, and my results or my answer is gonna be 0.0161 millimoles. Remember, anytime you take mils multiplied by molar concentration, you get millimoles. If you like to convert this into liters, you may, but if I were you, I would just leave it as mils. It's easy, and then you get your units here in millimoles. But you can see it's a 1-to-1 stoichiometry, and as such, the number of moles of the EDTA that remained up here are gonna be exactly the same, right? Because it's a 1-to-1 stoichiometry. So this is equals to also 0.016 millimoles. So the question then is, how much of the EDTA actually reacted, because this is what remained, okay? So the question is, how much of EDTA reacted, okay? And, from in equation 1, of course, in equation 1, Okay, and so this one would be equals to the number of moles that you started with. Remember in equation 1, if you remember, we had 5 mils of the EDTA, and I'm multiplying that, by the concentration that I had initially of EDTA, which is 0.0103. And so that's the amount that I initially actually added to my chromium sample. And then you do that, you get, whatever number of millimoles, that you get in this case, and then subtract, how much remained, which is what I have here, 0.0161 millimoles. And so how much actually reacted then is equals to 0.0354, millimoles. So that's how much actually reacted here, how much reacted. Remember, how much reacted is equivalent to, the moles, of chromium, that was actually present, right? So the moles or the millimoles of chromium that reacted, because the one-to-one stoichiometry, or that reacted, or that was essentially present really in the sample, would be equals to how much of the EDTA reacted, right? Which is 0.0354 millimoles. So you already know how much now of chromium, actually reacted. And so the question then, is calculate, the chromium in the sample. And to do that, you need to calculate the mass, of course, of the chromium. And the mass of chromium, that would be the mass of chromium, 3+, divided by, the mass of the sample, times 100. Okay. And so then the mass of chromium, would be the millimoles that are present, 0.0354 millimoles. And then of course I need to multiply it by the mass, the molecular weight rather, which is 158.36. And this would be in milligrams per millimoles, or grams per mole, but because I'm using, millimoles, I can keep it in milligrams per millimoles. And then I can divide it, now by the mass of the sample, which we already know up there. It was 2.63, which is equivalent to, 2630 milligrams, so that I can have everything in milligrams. And then I can multiply that, by 100%. So you can see the answer that you get, is 0.213, percent. And that's the amount of chromium that is present in the pharmaceutical formulation. So you can see how you do your back titration. Again, you determine the moles of the titrant in the second reaction is gonna be equivalent to the excess of the excess of the product here, and then you can determine how much reacted by taking this minus the excess, and that will be equivalent to how much of the sample actually was present. So another problem here, you've been given soda ash sample, and you're required to titrate it with HCl. So it's an acid-based titration. And the titrant, of course, here is a HCl, and so you end up dispensing 38.27 to titrate everything here in the soda ash sample. So that's the equivalence volume. So the question is calculate the percent sodium carbonate in the sample. As I've said before, maybe it's always good to start with the chemistry that is taking place. So the titration reaction. So you can see that I've got, the sodium carbonate, which is a key component, in soda ash. And because you're dissolving it, obviously it's gonna dissociate and produce, the sodium plus, two of them though, and that is aqueous, plus, the carbonate. And so essentially what you're titrating, is the carbonate. The carbonate is what you're titrating. The carbonate is what you're titrating, with the acid. Okay. And so the next reaction is, you're taking the carbonate and then you're titrating that with the acid. Typically it's a neutralization reaction, to give you water, plus, the carbon dioxide, gas, is generated. Yeah, so you see how important it is, to balance the titration reaction. Very critical to balance the titration reaction. So in our titration here, we added, 38.27 mils of the HCl. So the equivalence volume, the VE of the HCl that we added, is 38.27 mils. And in that case, then we can calculate, the moles, of HCl that was used. Which is gonna be equals to the volume, obviously. It's CV, that's the number of moles, that's how you calculate it. Concentration, it's already given up there. It's 0.1288 molar concentration. If I multiply it by the volume, it's 38.27, moles. And if I keep it in meals, if I keep it in meals, my my number of moles here is gonna be in millimoles. So I get 4.9292, millimoles. So the moles then, of carbonate, that was consumed or that was titrated, would be equals to, this number. You can see it's a 1 to 2 stoichiometry. It's a 1 to 2 stoichiometry. So the number of moles of the carbonate that was titrated would be equals to what I've calculated here, the amount of acid consumed, 92 millimoles. But again, you can see it's a 1-to-1 stoichiometry. I divided by 2. And when you do that, you're gonna get it's 2.464, millimoles. So now that you know the number of moles, you can calculate, the mass, of the carbonate or the sodium carbonate that is present in the sample. So it's gonna be 2.464 millimoles. And then I would multiply it, by, of course, the molecular weight. And the molecular weight of sodium carbonate, if you check, is equals to 105.988 milligrams per millimoles. And as I say, there's no reason why you cannot keep it, in milligrams or grams. So you're gonna see that the mass here is 0.2612 grams, or if you multiply that by 1,000, it's gonna be 261 milligrams. And so percent carbonate then, in soda ash sample is gonna be equals to 0.2612 grams divided by the mass that we started with, which was 0.2638 grams, multiplied by 100. And when you do that, you're gonna see it's 99.0% of sodium carbonate is present in that ore of soda ash sample. Remember when we did some work on uncertainty, and so this one asks you about uncertainty and error propagation. And so you've been given the molecular weight of silver nitrate is as such, and you've been asked to prepare a solution of silver nitrate. You weigh that amount and you dissolve it in a volumetric flask of 0.1 liters, and the uncertainty is given. And so the question is, calculate the molar concentration of the solution that you make, and most importantly, its relative uncertainty and absolute uncertainty. So the only key thing here is to remember how you propagate, the errors. And so in this case, I'm calculating the concentration of silver nitrate, and I know it's equals to the mass of the sample, 3.364, I think we all know that, plus minus 0.02 grams. And then we are dividing it, by the molar mass, which is 169.8729 plus minus 0.009 grams per mole. And we know the volumetric flask, that we are using, it's 1 liter. And so this is 0.1, plus minus 0.0008 liters, because remember what we had here was 100 mil, and so we've divided this by 1,000, and so equally we should divide this by 1,000 so that it can be in liters. And when you do that, you get okay, 0, 0. Actually, there's an extra 0 here. There should be 4 zeros, right? There should be 4 zeros, liters, okay? And so you can see my manipulation here involves division. There's division and, multiplication, okay? And because of that, then I should be using relative uncertainty. Remember that's what we said. If at all my computational manipulation involves division and multiplication, then I should propagate the error, the error that I put in my error propagation equation. The error squared 1, the error squared 2, and so forth. These errors should be relative uncertainty, if at all my manipulation is a division or multiplication. And so we go ahead then and convert our errors into relative uncertainty. So the error relative then that we put in our propagation equation is going to be equals to 0.002 divided by the number here, so that is the error divided by 3.364, and of course remember I'm squaring it, plus 0.0009 divided by 169.8729, again it's squared, plus Again, it's a division, so 0.00008 divide by 0.1. Again, you know, I square it, and then now I can do the propagation that way. And when you solve this problem, you know, you're gonna find is equals to 9.93 times 10 to the power minus 7, which is gonna give me, when you take the square root, 9.7 times 10 to the power minus 4. But remember, this is relative, right? This is relative. And so we need to convert this relative, you know, into absolute. Okay. And the way to convert that, of course, remember, is to multiply it, you know, by the determined value. So if you did the nitrate concentration, you would find is equals to, if you did this, you know, you would find the concentration you get is 0.19803 plus minus, and then the absolute uncertainty. And the absolute uncertainty is equals to the relative, 9.97 times 10 to the power minus 4 multiplied by that number, you know, the measurement, you know, which is equals to 0.19803. And now whatever you get here is absolute uncertainty, and it's gonna be in molar concentration, the same thing, you know, as your concentration that you calculated. And so when you do that, you're gonna find this plus minus 0.0002 molar concentration. All right. So in the statistics section, remember, we used the student's T for a couple of different applications, and I'd like you guys to go and review that. But one of the application of the student's T is to compare two different methods and determine if the results that you get from those two different methods are statistically different or statistically significantly different. So give you an example, you know, you've got a student here who measured the concentration of HCl, you know, by titrating it, you know, using, of course, a base, but they used two different types of indicators. You know, so they used two different types of color indicators, the bromothymo blue and the thymo red. And so they got these results, you know, the mean when they used bromothymo blue is written there, and the thymo red, you know, they got those results. And they did a lot of repeats, you know, to try and get those standard deviations. So the question is, are these two methods statistically different? Is the difference between indicator 1 and 2 significant at 95%, you know, confident level? And so remember, in this case, we need first, you know, to determine if the standard deviations are significantly different, if standard, you know, deviations are different. Because if they are different, you know, we're gonna use a different type of relationship than if they are not different. So you need to do what you call the F test, and you guys, this one was fairly simple, so I won't go into great details. You know, so you have to do the F calculated, you know, in the F test. And so you take, you know, the standard deviation of method 1, the standard deviation of method 2. Remember, the F value always has to be greater than 1. And so this numerator, you know, should be the standard deviation, you know, that is bigger. And so you get 0.00225 is a bigger one. You know, divide by 0.00098 and whatever ratio you get, is 2.296. Then you go to the table, and determine your f from the table, which again is fairly straightforward. You can check it out. And the f in the table, is 2.11. And so you can see the difference. In this case, the f, that I calculated is actually bigger, than the f, from the table. And so in that case, then the null hypothesis would say that the two standard deviation, the two standard deviations are significantly different, So meaning then you'll be forced to use a different type of calculation to determine if these means are different. Because the standard deviations are different, this means we cannot pull, the standard deviations. Remember, there is that simple relationship, where we pulled the standard deviations. Remember, where the t calculated, is equals to, the mean of method 1 minus the mean of method 2, divided by the s pulled, the standard deviation of the two methods pulled, multiplied by n and 2 divided by n, the summation of that. And that's how you do the t calculated if the standard deviations, were not significant. Okay, and remember the s pulled, is equals to that relation, which I'm gonna give you in an exam, s1 squared, which is the standard deviation of method 1, and 1 minus 1, that's not the degrees of freedom of the first method, plus S2, the degrees of freedom of the next method, divided by the degrees of freedom of both methods, which is that. Okay, so this is what you would have used if the standard deviations were not different, but right now they are different, so we cannot use those two methods. Instead, because they are different, we have to use this relationship. So you have to do the t calculated, as follows, and then the degrees of freedom as follows. And then now you compare, the t that you calculate, you compare it, with the t from the table. And if the t calculated is less than the t in the table, then you would say the methods are not different. And of course, we know how to use the tables. I'll give you the tables and you can do that. So in this problem, you're gonna see there's a difference, between the t methods. When you do the t calculated, you're gonna see the relationship is such that the t calculated, is greater, than the t in the table, and for that reason, they are different. So we also previously did work on, talk about standardization. And we said, of course, standardization, it's largely used to correct for matrix effects. So be able to recognize a problem, that uses standardization calibration. For example, this problem, an unknown sample of dopamine, which is a neurotransmitter, gave a current. So you're doing electrochemistry in this case, so they gave you a current of, that's a signal, and then after that you took a sample and you spiked into it 2 mils of a dopamine standard, And then in that sample, which was 90 ml, you diluted it to volume in a volumetric flask, and then you ran it again using electrochemistry, to give you another signal right there. So the question is, of course, calculate, what the unknown dopamine is. Yeah, the unknown dopamine in the sample. So take note of this, that this is a standard addition, calibration problem. And you've already done this in the lab, but the only difference in this case, this one is a single point, calibration. You don't have a series, of standards like you guys did with that you will do with the AAS lab. But in this case, it's a single point, calibration. All right, so remember the standard addition relationship. The standard addition formula, is equals to, the analyte initial divided by the analyte final after dilution. And of course, you've spiked it already with the standard and you've diluted it, so it's final. And you're getting, the signal. Maybe I'll just call it intensity or signal initially. And it corresponds, of course, to the signal of this guy finally, the signal final. So in our relationship here is going to be then the dopamine. That's what you're trying to analyze. And so the dopamine initial, that's what you're looking for, divided by the dopamine, final. And then you spiked it with the standard. Of course, the standard has to be dopamine as well, standard. And what you got here, 34.6 nano amperes is the current that you got. And then for your mixture of the standard and the sample, you got 58.4 nano amperes. So let's substitute this then, so the dopamine initial, allow me just to use D, and then the dopamine initial, multiply. Remember, the dopamine final is equals to the dopamine initial multiplied by the dilution formula, the dilution relationship here, which is 90 over 100. Okay, and then you can see the standard, its concentration, again it was diluted, its concentration was 0.0156, and you had 2 mils of that, so volume initial divided by volume total, which is 100 mil. And then of course the relationship here, when you get that ratio, it will be 0.5924. And so you can now solve this relationship because the only thing that is not known is the dopamine initial, okay? And so the dopamine initial, if you sort of extend this problem, is gonna be 0.5924, and then of course you take this, multiply on this other side. So it's gonna be 0.9 di, 0.9 plus whatever I get here, is 0.000312. And so after that, I can solve for the di, and you're gonna see in the end, the di, of course, when you take this to the other side, it becomes negative and so on. Of course, a simple algebra, that one you have to know. So the di then, is equals to 0.0000394, 18, and that's the molar concentration. But all you want it in millimoles, or rather in millimolar, is 0.394 millimolar. So the next problem, it's an internal standard addition problem. Now remember the purpose of the internal standard. The purpose of the internal standard, is to correct for instrument irreproducibility. Instrument irreproducibility. And so the question is, how do you solve this, single point internal standard problem? And you guys have already done this kind of problems, with the GC. With the GC lab, it was an internal standard problem, but of course with the GC lab, it was multi-point, calibration. All right, so remember the internal standard relationship, is the analyte signal divided by the concentration of the analyte, which is equals to the response factor, the so-called F, multiplied by the standard signal. Remember now this is the internal standard, divided by the concentration, of the standard. Of course, you can move around the relationship for it to look like this, the standard. If you multiply this side by the standard divided by the analyte concentration is equals to the response factor, standard signal, divided by your analyte signal. All right, so if you look at the problem that we have, we've got the concentration of the standard is given as 94.0. I think it's nanomolar. Yeah, I think it's nanomolar. 0.0 nanomolar. And the concentration of the analyte, which is the iodoacetone, it's 80.0 nanomolar. And so the first thing you need to calculate is the response factor. And the standard signal and the analyte signal is already given, as a 0.71. So it's 0.71, but remember it's an inverse. Whatever is given is the inverse. Okay. So when you get this inverse, it's gonna be the 1.4. So it's the 1.40. So the standard signal divided by the analyte signal is actually 1.4. So you get the F, the response factor. When you calculate, you're gonna see a 0.571. Knowing the response factor, now you can calculate the unknown, and the unknown is already given as follows. You just substitute it in the problem there. The standard is 930 nanomolar, and then you have to calculate the analyte. You already know the response factor, and you already know the ratio, of the analyte to signal, and you've been given that to be 0.826. Of course, the ratio that you've been given up there, is 1 to 1.21. But this one is given, for analyte over the signal. So you need to take the inverse of that. And when you do that, you're going to get, the 0.826. And so after you do that, you can just calculate then. You've got only one unknown, the concentration of the analyte, then you can see is equals to 1971 nanomolar. And that's what you get. That's what you get. And of course, you can convert it, into micromolar, by dividing it by 1,000. And lastly, for this lecture, figures of merit. I think I spent quite a lot of time talking about the figures of merit, and maybe it's very, very critical, for analytical chemistry, for you guys to understand how to do the manipulations for figures of merit. So give you a data set, that looks like this. You're doing AAS, just like you're gonna do using the copper lab, which is atomic absorption spectroscopy. and then you run your calibration. These are the concentrations, and you get your signals, and in each one of them you repeated it 5 times. And so the question is, number one, from this simple calibration you can get lots of figures of merit. Question number one, calculate the calibration sensitivity. And of course the difference between the two graphs is, in one case you've got all the data points, and then in this case you don't have these data points. Reason being, it seems to be deviating from linearity. Okay, you can see it's deviating from linearity. So we omitted it when you are calibrating here, and you can see the regression coefficient is a lot better, 0.99, very close to 1, which is what you want. So from this method of calibration, you can determine the calibration sensitivity. Remember, the calibration sensitivity is nothing but the slope. So let's just use this calibration. The slope is 3.26 units per ppm. So that's a calibration sensitivity. That's all what you need to do. Remember, on the other hand, analytical sensitivity is a calibration sensitivity. Calibration sensitivity divided by the standard deviation of the measurement. The standard deviation of the measurement. Maybe some of you are gonna ask, which measurements do I do? So what you're gonna need to do is come here and look at the average standard deviation. Okay, average standard deviation. So you average this and when you do that, you just take the 3.26 divided by the standard deviation of the measurement. That's what you call analytical sensitivity. So take note of that difference. Okay, remember, again, the steeper the slope, because you're saying calibration sensitivity is just the slope, which is this. The steeper the slope, the better the analytical method, the more sensitive the analytical method. And so question C is limits of detection. So the limit of detection, if you check the notes, LOD, remember we said is equals to the signal of blank plus 3 times standard deviation of blank. Okay, and this one is a limit of detection in signal form. So you can see the signal of the blank, you can see it's right there. So that's all what I'm gonna need to use, the 0.025. So 0.025, that's a signal of the blank, times 3 times standard deviation of the blank, which is given right there, 0.0111. 0.011 is a standard deviation of the blank. Okay, and whatever answer you get, that's a limit of detection, but you can see it's in signal units. If you've been asked to calculate the concentration, specifically concentration limits of detection, or what you're gonna need to do is take the 0.025 plus 3, 0.011, essentially these signal limits of detection, and then you divided it by the calibration sensitivity, which is a slope. And I think we had it before at 3.26 and that is units. This is units per ppm, and then you can see the answer that you get is gonna be in ppm, and that's why we are calling it the concentration limit of detection. Now remember, again, if you're doing limit of quantification, is exactly the same as limits of detection. The only difference is you replace this with 10. Okay, all right, so take note of that. The limit of quantification is gonna be 0.025 plus 10, 0.011, and of course those are the units. If at all you've been asked to calculate the signal limit of detection, divide by 3.26, units per ppm, and you can see the answer you get, is gonna be in ppm. So dynamic range refers to this. In your calibration, you've got the concentration, maybe ppm, and you've got up here, you've got the signal, you've got your calibration. Right here, you've got the limit of linearity, and right here, you've got the limit of quantification. Right there, you've got the limit of detection. So dynamic range, refers to limit of linearity divided by the limit of quantification. Okay. And so the question is, how do you calculate, the limit of linearity? You just look at it right from the table, right from the data. So you can see the limit of linearity in this case, is gonna be this guy. The 12 is the last data point, where you're getting a good linear relationship. So you can see the limit of linearity in this case is actually gonna be 12. Okay, and so the limit dynamic range then. Dynamic range then is gonna be 12 divided by the limit of quantification, which you calculated, up there. Whatever number you get, you get that ratio, and that is your dynamic range. So that is the range at which your concentration is proportional, to the signal. It's linearly proportional to the signal. And so please take note of, all those figures of merit, that I've shown you how to calculate.